How's it going? Today we're going to talk about start chapter 7. Talk about polar coordinates. What I need you to understand about polar coordinates is it really is just another way of doing the same thing that we've done before. It's just another way to graph, basically, is all it is. Throughout your life, you have done a lot of plotting points and graphing different things in what we call the rectangular coordinate system. Points like the point 4, -3. In the rectangular coordinate system, we have an x-axis and we have an y-axis. And basically, we plot everything in terms of x's and y's, right? So we go right 4, down 3 kind of thing. Well, the polar coordinate system is just another way of describing or another way of getting to a point. Instead of an x and a y, we have an r and a theta. We have a radius and we have an angle. So the angles work just like before, like we would go to the 210-degree angle, and then along that line, we would count out 1, 2, 3, 4. Okay, so the rectangular coordinate system is just a different way of getting out to the points. Kind of to show you what graph paper really looks like. If we were in class, I would actually hand you paper that kind of looks like this. If we wanted to plot that same point of 4, 2, 10, we would go to a 210-degree angle. I realize this is in degree or in radians, so maybe, instead I give you one that looks like this one, right? So that's the same idea. We go to a 210-degree angle, so we go out to 210, right? So we're on this line right here. And then we just count out 1, 2, 3, 4. So the rectangular point, or the point 4, 2, 10 would be right there, right where my mouse is located right now, right? So it's just another way to get or describe how to get 2 points. The easiest way to understand kind of the main difference is I equate the rectangular coordinate system kind of like giving directions to somebody's house. You kind of have to follow the roads. We go east 4 miles and then we go south 3 miles kind of thing, right? But we have to follow those roads. The polar coordinate system is kind of more how the bird flies. He goes, he flies on a certain course, could be 210 degrees. And then along that course, he flew 4 miles kind of thing. So kind of that might help illustrate kind of the difference. One of the nice things or kind of weird things sometimes when you start plotting some points, you might have different ways of getting to the same point in the polar coordinate system. So for example, the point 450. So we would go to the angle 150 degrees, which would be right here with a 30-degree reference angle, right? And then along that line, we'd go out 1, 2, 3, 4. So that point would be right there, right? Well, the point 4, sorry, I forgot the negative. The point 4, -210 would actually be in the same point, because a negative 210-degree angle, we'd go down, there's negative 180, we go up 30 more. So the angle is a coterminal angle with 150, right? It ends in the same spot. And then again, we would go out 1, 2, 3, 4. So again, these two angles actually get you to the same place, right? And actually, you can have now what we call negative radiuses when you deal with the polar coordinate system. The only difference is we kind of walk backwards. So an example would be a 330-degree angle. So we go almost all the way around, right, for a 30-degree reference angle. So there's a 330-degree angle. But because we put a negative radius, instead of going 4 in that direction, we actually extend the line backwards and we go 1, 2, 3, 4 in the opposite direction, you know? So we're think of it like flying in reverse, right? So the bird points in the direction of 330, but it actually kind of moonwalks and goes backwards 4 miles instead. But again, we end up in the exact same spot we did before. And we could have a fourth one get us to the same spot because we could do a negative 30-degree angle, which would be that angle right there. And then again, because the radius is negative, we can extend that in the opposite direction and go 1, 2, 3, 4 again. And again, we end up in the same spot. So actually, all 4 of those angles get you to the exact same spot. And you can do that with any point in the polar coordinate system. Some people think that's a good thing where you have multiple ways to get to the same point now. Other people find it a little bit more difficult because now you have multiple ways of doing the same thing. Where in the rectangular coordinate system, like this point here, that 4, -3, there really is no other way to get to that specific point of 4, -3 other than, you know, right 4, down 3, okay? So that's one of the differences between them. Now, we do have to have ways of going back and forth. Just like any other type of systems, you know, we have, like when we do degrees and radians, we have to have ways of getting back and forth between the multiple systems. So we've done this in the past where we have things that deal with this, right? If we have cosine is equal to x over r, that's an established fact we've done a long time ago, where any angle, you know, is adjacent over hypotenuse kind of thing. So we have these cosine is x over r, sine is y over r, tangent is y over x. We also have x squared plus y squared equals r squared. So one thing we can do is we can take that equation, that cosine of theta is equal to x over r, right? And we can basically rearrange that just by butterflying this to where x, I'm going to write it backwards just to make it a little easier. X is actually going to equal r times that. It's going to help us go back and forth between the rectangular system to the polar or vice versa, okay? And we can also do the same thing with sine of theta is equal to y over r. If we butterfly that, we can get to the point where we know y is equal to r sine of theta, okay? So what those will come into play, what those will make it easy is when I want to, let's say I have I'll just do this example right here. When I have this, I have an r and I have a theta, right? I have a radius and a degree, but maybe I don't want to do it in polar coordinate. I want to figure out that point, and I know it's in the third quadrant because 210 degrees would be down here. If I wanted to figure out what the polar coordinate, the rectangular coordinate equivalency of it, instead of having an r and a theta, if I want to turn it back into x's and r's, I can just use these two rules, where if I want to find the x value, all I have to do is take the r and multiply it by the cosine of theta. So I can go x is equal to 2 times cosine of 210 degrees. Now, here's where hopefully you remember your table, right? Cosine, that's a 30-degree reference angle. Cosine of 30 is equal to square root of 3 over 2. I'm in the third quadrant. Cosine is negative in the third quadrant, right? Now, all I really have to do is multiply that by 2, and I know x will just equal negative root 3, okay? So I know in the rectangular coordinate system, the x value is going to be negative square root of 3. That's how far over here I'm going. right? If I want to find the y, I just use r is equal to r sine of theta. So my y would equal 2 times sine of 210 degrees. Well, again, it's a 30-degree reference angle. Sine of 30 is a half. It's in the third quadrant, so it's negative. I multiply those together, and I get y is equal to -1. So I know the coordinate of that point would actually be negative square root of 3, -1. So if I wanted to convert back and forth, I can do that. If I had one that maybe I couldn't use my table, right? But I'm still going to do it the same way. I'm going to say x is equal to 5 times the cosine of 110, right? Now, we're in the second quadrant, so that's important to keep in mind. But sometimes I do need to just grab a calculator. Make sure you are in the correct mode right now because we are dealing with degrees, so we got to make sure we are in degree mode, right? So I can just type in 5 times the cosine of 110, and I would know my x coordinate would be -1.71. And I can do the same thing with my y and just do 5 times the sine of 110. And if I do that same thing, but instead of pressing the cosine button, if I just press the sine button, I would get 4.69. So I would know this point, I can plot it by going 110 degrees, which would be just a little past 90. And I go out 1, 2, 3, 4, 5, way up here somewhere, right? That's also the equivalent of the point -1.71, 4.69. This would be the rectangular coordinate of that polar coordinate, okay? So that's how you go from polar to rectangular. But what about rectangular to polar? Well, if I go back to these rules, let me get my calculator out of the way here. If I go back to our rules that we've established in the past, I need a way of turning a x and a y into an r. Well, there's one right there. I know that r will just equal the square root of x squared plus y squared, right? Now, you do have to remember here that we're taking a square root, and a square root can be positive and negative. And I know we've said in the past that r's can't be negative, but in this polar coordinate system, r actually can be negative. So it's important when we take our square root, we have to keep in mind, is our answer getting ourselves to the correct spot? What I mean is, if you take into consideration something like this, if I use the point 330 and then +4, that'll get me down here in the fourth quadrant. It's not where I want to be. So just remember what quadrant you're trying to get to, and that'll help us decide positive or negative. And then we have a way here of finding our angle, because if I have my y and my x, so I know that tangent, or the inverse tangent of my, let me rewrite that. My angle will equal the inverse tangent of my y over x, right? So again, it is important to remember, whenever we do an inverse anything, we have multiple answers. So it's just important that when we get an answer, we actually double check, make sure it's getting us to the correct quadrant we want to get to, okay? Because it's easy to make mistakes in the polar coordinate system. So let's take, for example, this. I have an x and a y, and I want, let me put this on the side here so we can use it, and I want to turn this into an r and a theta, okay? So that's my goal here. Well, how do we find the r? The r is just going to equal the square root of 3 squared plus -square root of 3 squared. Well, 3